Here's the first question. The blades of a blender rotate at a rate of 6,500 RPM. When the motor is turned off during operation, the blades slow down to rest in 3 seconds. What is the angular acceleration? So how do you proceed with this? I gave you the blades of a blender. They are going at 6,500 RPM and it's turned off and comes down to rest in 3 seconds. Think of a blender. Okay? Comes down to rest in 3 seconds. So what is the data that's given to you so far? Is omega initial given? Yes. Yes, that's 6,500 RPM. Omega final, 0. Yeah. Time, 3 seconds. So you're given all the details, but are they in favorable units? You need to convert RPM to radians per second. Because you can't work with RPMs, because that's not an SI unit for omega. Omega. Alright, so 6,000. So how do you convert revolutions per minute, radians per second? Revolution, each revolution is 2 pi radians, so multiplied by 2 pi. And then per minute to per second, divided by 60. So multiply by 2 pi and divide by 60, and that should be the radians per second. How much is that?
680.6.
680.6. So you have that, and then you should be able to do it. So the equation that we're going to use is omega final equal to omega initial plus alpha t. Substitute and get the answers. Anyone has the answer? Answers? Anyone? 0 equal to 680.6 plus 3 alpha. So alpha is equal to negative 226.8. The negative sign tells you it is decelerating because it is coming to a halt. If there are no other questions, I'm just going on. Yes, everything's good? A bicycle with tires 68 centimeters in diameter travels 8 kilometers. How many revolutions do the wheels make? A bicycle wheel has a diameter of 68 centimeters and it travels 8 kilometers. How many revolutions did it make? How many times did it spin? So what are we trying to find? Yeah, but in all those equations, we don't have a number of revolutions. What is the nearest to it?
Oh, I was going to say how many tire lengths.
There are different ways of doing it. What you said is also acceptable. Angular displacement. That's what we are looking for. Once you get the angular displacement in radians, then you can convert it to revolutions. Right? So we are trying to find out theta. I'll show you both ways of doing it. What you said is also correct. So we want theta. And we have the radius. What's the radius?
34 centimeters.
Yeah, but change it to meters. So that's the radius. And you have the arc length, the total length. How much is the total distance covered? 8,000 meters. Again, kilometer is not a favorable unit. So once you have this, you can find the theta. Theta is equal to S over R. And that will be 8,000 over 0.34. That will get you the answer in radians. And then what do you do from there on is divide by 2 pi. You get your answers and divide by 2 pi. That will be your number of revolutions. So what is this answer? 3,000? What?
3,744.8.
Revolutions?
Yes.
No, he's asking for that answer. That one is. That
Possible.
one's 23,529.
This is 23,000?
529. 529.
And then you divide by 2 pi. Yeah, you should be right.
And that's 3,744. Yeah.
Okay? An automobile engine slows down from 4,500 RPM to 1,200 RPM in 2.5 seconds. An automobile engine slows down from 4,500 RPM to 1,200 RPM in 2.5 seconds. Calculate angular acceleration. So it slows down from 4,500 RPM to 1,200 RPM in 2.5 seconds. What is the angular acceleration? Again, we are using the same equation. I'm not going to work it out. Tell me the answer. You know what, again? You have to change this to radians per second. Change it to radians per second. And then use it, and we can find out. Yes.
Negative 22 radians per second squared.
I don't know. Is it right?
Negative 22 pi.
Huh?
Negative 22 pi radians per second
Or
squared.
22 pi. Get it all together.
Negative 22 pi
Change it.
I got negative 132. Yeah, I got that.
Okay. Is it all the answer everybody is getting? All right, good. The next part of this question is asking the total number of revolutions the engine makes in this time. How many revolutions does it make in this time? So you're looking for error. And if you don't want to depend on this answer, then we can use this equation. That'll get you theta, right? Omega final, you know it. You know the numbers there. So pick that up and multiply it by 2.5, and that will be the number of radians. But the question is asking how many revolutions does it complete in that time, so we have to divide by 2 pi. How many turns? How many radians? Omega final plus omega initial divided by 2 times 2.5. Yes,
746.
radians, and then convert it to revolutions now, divided by 2 pi. Remember to put the 2 pi in parentheses, okay? That's a very common mistake. So that divided, how much? Yeah. So 119 revolutions it makes before it comes to 1. Now before it changes the speed.
I just thought he could be shifting from like first to third gear also if it was going from 4,500 to 1,200.
downshifting the gears?
Or no, upshifting. He was in third, and he went, or if he was in first and he went into third or fourth, it probably dropped down to about, or maybe, yeah, probably from first.
No, we are talking about the engine speed,
Yeah.
not the gear speed.
Yeah, I know, but like if he was driving first, which is gonna happen at a pretty.
Oh yeah. This can happen, yeah. Or it can happen just naturally. Just release it and then it will come down also. The engine speed will come down eventually. If you just release the gas, then automatically the RPM is going to drop. Okay, so the more you supply the gas, it's supposed to increase the RPM. You can see the RPM meter going up when you're speeding up. But when you're actually idling, it should be pretty low. Okay, so that could be an idling sort of thing, and that will be the, depends on the gear too. A 55 kilogram person riding a bike puts all her weight on each pedal when climbing a hill. So a 55 kilogram person riding a bike puts all her weight on each pedal when climbing a hill. The pedals rotate in a circle of radius 17 centimeters. The pedals rotate in a circle of radius 17 centimeters. So those are the pedals. Sort of thing. And on the other side, the same way. So the pedals the pedals rotate in a circle of radius 17 centimeters. What is the maximum torque she exerts? What is the maximum torque she exerts? It's asking for the maximum torque. So obviously when this pedal is here, right? And then she uses a weight. So what is happening is the pedal is here, the pedal is there, and she's applying her weight straight onto the pedal, like stand on the pedal at this point. So what is the force? She's 55 kilograms, so 55 kilograms is her mass, and the force she's applying is her weight. So 55 times 9.8, and the perpendicular distance, maximum one, is this, which is 17 centimeters converted to meters. So what's going to be that? What is the maximum torque?
91.6.
So 55 times 9.8 times 0.17. How much?
91.6.
Newton meter. 91.6 Newton meter. That's the maximum torque she's applying. Second part of the question says, how could she exert more torque? Are there ways of exerting more torque? Yeah.
You could have a longer, like the 17 centimeters.
Yeah, if there is a way to increase the pedal, but you can't increase the pedal on the drive. Yeah, you're already driving, and then, yeah.
I wouldn't necessarily increase the torque. Well, actually, I guess what if she had pedals that she had biking shoes that she had to clip in, so that she was also pulling up rather
Yep,
than just pushing
that's a
down.
good point. Yeah, so if your legs are locked up with the pedals, and as she's kind of putting her weight on one of them, if she can apply a pulling action on the other one, that's wonderful. It's like opening this tap. If I open the tap with just one finger, it's going to be hard. But if I just support it from the other side, it becomes easy, because then you're doing two torques at the same time. So when she's applying her weight on one of them, you are pulling it from the other side, which actually kind of adds more torque. Any other? Yeah.
She wears a heavy backpack to increase her mass. She wears
She
or,
I mean, her mass is kind of decided. before she starts driving, she's not going to carry an extra load as she is. Yeah,
Jump on.
jump on it. Yeah, she's kind of hopping on it like this, like throw the weight on it. Yeah, that way, if she's jumping on it, she's able to apply more impulse on the pedals, which means more force she's able to apply for the same distance. So when you kind of jump on it, you end up creating more torque. And so we do that. Then when you really need to kind of climb up on that hill, you end up doing all those things. By all means, you want to increase the torque. Yes. Yes.
Scientifically, like why is she applying more by jumping? Like her mass and acceleration is still the same.
Yeah, but when you jump, just standing alone, like for example, when I stand on the floor, how much force am I applying on the floor? My weight.
Yeah.
But when I jump, can I apply more than my weight?
Yeah.
Why? Because when you jump, it's like a change in momentum. You're creating a change of momentum. And when you create a change of momentum, that will cause forces. So change of momentum causes forces. Something sitting idle is fine. I can have a hammer sit on my hands. It's perfectly okay, right? My hand is able to bear the weight of the hammer. But if I do that, then that's going to be harmful. Okay, if I drop it on my hands from even a little height, that's going to hurt because that's going to create more force. Get it? Next one. Calculate the moment of inertia of a bicycle wheel 66.7 centimeters in diameter. Calculate the moment of inertia of a bicycle wheel 66.7 centimeters in diameter. The rim and tire have a combined mass of 1.25 kilograms. The rim and the tire combined has a mass of the rim and the tires is 1.25. Go ahead. Tell me the moment of inertia of this bicycle wheel. Pretty close. What's the answer? What's the formula? Moment of inertia of a bicycle wheel. What do you consider this as?
I guess it would be a ring.
It will be a ring. So it's mr square. Now, radius is not given, but diameter is given. So what you can do is, so you can do m d square over. Yeah, instead of messing up with this number, you can leave it as diameter. And then you have the 4 coming in there. So 1.25 times 0.667 squared over 4. That's why I brought the 4 back here. See, remember when you did the vernier caliper and all that, you did the volume of a cylinder. It's actually pi r square h, but actually I didn't use that formula. I used pi d square h over 4. Remember that? That's because we are not measuring radius, but we're measuring diameter. And so if you want to use the raw data of the diameter into our equations, that's a safer thing to do than to divide whatever and then get the radius and then use that corrected number. Yeah.
Why do we ignore the spokes of the wheel?
That's going to be my next question. Wait a minute. So what's the answer for this? Kilogram meter square. The unit is kilogram meter square. So 0.139 kilogram meter squared. All right. The second part of the question says, the mass of the hub can be ignored. Why? The mass of the hub can be ignored. Why?
Does this mean there's that
Has
radius?
small radius.
Can.
The hub can be ignored.
Because it's a catch.
Because that's the point that it's incredibly close to the.
Yeah, that's so the radius of this is very, very small. So even this hub, even if the hub has a mass, since the radius is so small, it doesn't have much moment of inertia compared to the other one. So moment of inertia is mr square. So for the hub, it'll be probably mr square over 2 because it's a kind of solid cylinder, right? But its r is so small that it won't really make a difference to this number. And that goes to explain why the spokes are also negligible, because the mass of the structure here is much, much more than the mass of the spokes. But if you're given the mass of the spokes and you're supposed to include it, you can include it. But if you're going to use, include this one, then we have to use the right equation for the spokes. Next question. A grinding, no. A potter is shaping a bowl on a potter's wheel, rotating at constant angular speed. So we have the potter's wheel. It's spinning at a constant angular speed, and the potter is actually working on a pot, obviously there. So a potter is shaping a bowl on a potter's wheel, rotating at a constant angular speed. The frictional force between her hands and the clay is 1.5 total. The frictional force that she's applying is 1.5 newtons total. Total, meaning she can use 2 hands or 3 hands, but still the total friction is 1.5. Okay? So the total friction she's applying on this, like, so as this is spinning like that, like imagine that's a potter's wheel. She's touching like that. So the total force is what is indicated as 1.5, which means even if she touches one hand or like that, the total force is 1.5. Then how large is her torque on the wheel? If the diameter of the bowl is 12 centimeters, the diameter of the wheel is 12 centimeters. How large is the torque? How large is the torque on the wheel? Huh?
12 centimeters is the wheel
Of the pot. That is 12 centimeters diameter. She's applying 1.5 like that. Oops. Okay. All right, so you get it? Yes.
She's always pushing like towards the middle. Wouldn't that be 0?
No, I mean she's touching like this means the frictional force is tangential. The force is not going to be it's basically the friction that is coming in. Because the perpendicular for downward, the normal force is not going to matter. It's a friction that matters. So when she's touching like that, the friction is what actually matters. That's why it slows down. So if this is spinning, and if I do that, it is actually good. I'm going to hold it like that. It's going to cause it to slow down because of the torque. How much? The force is 1.5 and the perpendicular distance is 0.06 and that is 0.9, right?
0.09.
0.09 Newton meter. And is this a positive torque or a negative torque? It's supposed to be negative torque because it is supposed to slow it down, right? It doesn't matter. Yeah, it's a slowing down thing, so whichever direction it is, don't worry about it. So it is going to be slowing it down, so it's a negative torque. The second part of the question says, how long would it take for the potter's wheel to stop if only torque acting on it is due to the potter's hand? The initial angular velocity of the wheel is 1.6 revolutions per second. And the moment of inertia of the wheel and the bolt together is 0.11. Yep. So now it says, how long will it take for the entire wheel to come to a halt? So this is going to be our initial angular velocity, and the final angular velocity is 0. And the moment of inertia of the entire thing is given to you, and the question is asking for how long. So you have omega initial, you have omega final, you have you need the time, you need one more thing. What can you get from angular acceleration? So yes, once you have the torque, you can find the alpha by using the equation torque is equal to I alpha. So alpha is going to be torque over I, which is negative 0.09 over I, which is 0.11. That's going to be the angular acceleration. It will be a negative answer. So negative 0.8181.
Yeah.
Okay. 0.8181. That's going to be the negative. This is radians per second squared. So you got alpha. Once you have alpha, you have omega initial. Okay, again, omega initial is not the right units. Change it to radians per second. So each revolution is 2 pi. So multiply 1.6 with 2 pi seconds is perfectly okay. So 1.6 times 2 pi, what is it? Now you're all set. Just apply the equation. Omega final is equals to omega initial plus alpha t. Omega final is 0. Omega initial is 10.05 minus 0.8181 t. And then t is what? How many seconds it takes for it to come to a halt?
$12.3.
12.3 seconds. Okay. The next one. Yeah, so you can see the concept is, so you can see the parallel nature of the two, linear motion and rotational motion. It is pretty much the same thing. Instead of acceleration, you're talking about angular acceleration, and everything else is basically the same style. The only difference is this is rotating and the other one is going in a straight line. A helicopter rotor blade can be considered a long, thin rod. So, helicopter rotor blade can be considered a long, thin rod as shown there. If each of the three rotor blades is 3.75 meters long, and has a mass of 160 kilograms. So each one is 160 kilograms, and 3.75 meters long. Calculate the moment of inertia of the 3 rotor blades about the axis of rotation. Calculate the moment of inertia of the 3 rotor blades about the axis of rotation. Now, what formula? They said it can be considered as a thin rod, like this. ml square over 3, because it's rotating about one end. So the rotor blades are not spinning like this, instead it's spinning like that. It's going at one end. And the formula for that is ml square over 3 for each one. So the moment of inertia of each one is ml square over 3, but there are 3 rotor blades. So the total moment of inertia is going to be is ml square over 3 times 3. So that is ml square, substitute. 160 times 3.75 squared. And that's the moment of inertia. How much?
2250.
To 50 kilogram meter square. The second part of the question says, how much torque must the motor apply to bring the blades up to a speed of 5 revolutions per second in 8 seconds? How much torque is needed to bring the blades to a final angular speed of 5 revolutions per second in a time of 8 seconds? Go ahead. So we have omega 3, omega final is equals to omega initial plus alpha t. Omega final is 5 revolutions per second, 31.4 equal to 0 plus alpha times 8. So alpha is equal to 3.923 radians per second square. Now you use the equation torque is equal to I alpha. You have the I, you have the alpha, multiply them and get the torque that is needed. Inertia of rotation. See, when an object starts moving, it has what is known as the inertia of rotation. Let me put this safely here. Okay. Yeah, so this one right now has just inertia, right? Mass. So if I'm going to take this and move, it's just mass. So if I have to accelerate it, I just have to apply a force and everything is good. But if the same thing is now spinning like this, it is a different thing altogether because it just does not have only mass, it has inertia of rotation because it's spinning also. It has the inertia of rotation. So what happens is if I'm just walking straight with it, it's perfectly okay. The problem comes only when I try to change its direction. So when I change its direction, then things are different. Now, a plane's propeller has that issue. A single propeller plane, which way does it turn? This way or this way? You're the pilot. To the right, like this? Are you sure of that? Yes, I think it's clockwise. Yeah.
Then the one I play was clockwise.
So when you're sitting like this, it goes this way, right? Okay. So that's the propeller blade that is spinning like this. And when we try to take off, what happens is we change the direction, and it does not like to change the directions because it has inertia. So it refuses to turn. So what happens is the consequence is I'm going like this, I take off, and it goes this way. It actually goes that way. You're trying to take off, and the same thing while coming down. While coming down, it twists this way. So the one who is actually flying has to really take care of that part. I was not aware of this, the practical part of it, when I did the flying first time with Tim. When I did it first time, he just gave me the control and said, okay, just go. And I was fine. On the runway, everything was fine. On the runway, everything was fine. And as soon as he said, okay, take, and when I started taking off, the plane was like already going to the right. And then I said, I think it was right. And I was trying to fight hard to keep it because I didn't want to turn all the way around. So as soon as it took off, it was like leaning to the right, and I was like trying to balance it by twisting it this way. And yeah, and there was a little miscommunication at that time. Then I asked him at that time, so I said, okay, now which way should I turn? Because it's already leaning to the right, I don't want to struggle so hard, so which way we should go? Then he said, oh, you can take a right. And then I said, all right, in that case, fine. So then I started taking to the right, and after taking the right, he immediately, oh my God, it should have me to the left. And then he just contacted the control towers immediately and told them that, like, we have taken the right, is it okay, or should we turn to the left? They said, okay, it's okay, just keep going. So we wanted to go to Frankfurt. So instead of actually turning this way, that was the initial instruction, we turned the other way. So there can be confusions like that. Anyway, so I realized the change of directions and all that. So when it has inertia, it retains its position. See, when it's spinning like this, it can retain its position, is not falling off because of this. No matter what I do, it stays in that same position. It doesn't want to move from its original position. If I keep it like that, it stays like that. It's like a memory foam because it has inertia.
You swing it again.
Huh?
You swing it again.
Swing it again.
Yeah, it's very nice.
Now, is there any volunteer here to test this out? Come on, Jake.
I love volunteering. I know what I'm volunteering for.
Hold it. No. Are you left-handed? Come this way. Hold on. Don't put that thumb inside. All right. So what he's going to do is, now this is not spinning right now. It just has inertia. So what are you going to just lift it up? Yeah, but make sure it's not touching your head. Okay. Bring it down. Quickly. Down. Quick. Good. He is strong enough. So he is able to do this. It just has mass, nothing more. But now I'm going to spin it, and he's going to do it at the same speed. Just watch his expressions, okay? Go. It doesn't obey. I mean, he wants to take it up, but he's twisting on the left and right. Look, it's going that way. Bring it straight up. I'm trying. It's a good exercise for the hands. Anyone else?
Donnie.
Come, Dominic.
He's gonna do it.
If you can just take it straight
Big man on
without
campus.
any deflection at all.
Just going on the tube, Donnie.
Get it,
Don't
Don.
bring the
Get it,
thumbs
Don.
Go up. Yeah, make sure your finger doesn't go inside, because once I was actually asking someone to do it, because it was tough, he popped his thumb inside, and he actually cut. I was sent him to the nurse. So, yeah, because he popped it. So it's dangerous. So make sure that doesn't happen.
Donnie, stick your thumb in there.
And down quickly, fast. Good. No deflections throughout perfect.
That's a all forms in action.
Oh, there it is. Light work. Light work for Don. Killed you, man.
Dude,
Oh shoot! Just a little harder than it looks. Alright, I'm done.
Okay.
Orbit. You just need to feel it. It's like
Jacob, you got the hot
hold it up and show him like.
You good? Yeah. Quickly.
Yes, Char.
Okay.
Big boy.
Another one.
It just takes you in circles almost. All
So
right.
if you do it slowly though, will it have like the same kind of effect, or if you do it slowly, will
It still has to. You have to apply.
you just
because
have to
you
apply
have to, like-
more force?
You have to apply
On
it
the way,
all
okay,
in order to get it going. and stuff.
Oh,
Or stand like this and you just
We went faster.
you stand straight like this.
Every day I just curl spinning back to virus.
For that? Okay.
Oh no.
Oh, this might get ugly.
This is gonna be.
Make sure the gun doesn't go anywhere.
I hope it does.
I'm ready. I got it.
What is that?
It's a real life Beyblade.
Go to the right. Go to the right. Once you bring it to that position, then it's easier. But the changing from here to a right angle, that's the hardest part.
What if like we took this and like tried to make like circles in with your arm?
I think if you do this, I think it should be okay. I think it should be okay this way.
Try
The only thing is, as long as the angle is not changed, if you're doing this, I think it should be okay. The only thing is that. The angle.
Oh, yeah.
Only thing is when you see when it's changing.
Yeah, you got it. Oh man!
Oh, I'm
Get this like.
It's like the Disney Channel.
this way.
I'm Ryan Fiddle, and you're watching Disney.
All right. Now,
That's a flow rider.
you got it. Next problem. Inclined plane. Yeah, you've done problems like this before. So we're keeping a ball here, a bowling ball, okay?
Yes.
And the height you're releasing it from is 2 meters. And if I ask the question, well, I've asked this before, how fast is it going when it is here? How fast is it moving when it is down there? What do you do? Any ideas? You've done this before. Yes.
You have like the potential energy.
You have the potential energy that is getting converted to kinetic energy. But unlike what you have done before, you have learned something extra now. So now you have to think of it in a different way. Now, this ball, as it starts rolling down the hill, what kind of kinetic energies does it have? And translational, both. This wheel, if it is just going like this wheel, if it is just going like this, what kind of energy does it have? Just translational kinetic energy. Translate. What's the equation for it? 1/2 mv squared. But if this is a wheel that is spinning and moving forward, what energies does it have in addition? Rotational kinetic energy. So This thing, when it goes from here to here, what energy is it losing and what energy is it gaining? It's losing GPE, all right? GPE lost is equal to the kinetic energy plus the rotational kinetic energy gained. It's gaining both. At this point, it is not moving, no speed. At that point, there is a speed. So nothing else is given to you. The diameter, nothing is given to you. You're supposed to find how fast it's going there. And here is how you do it. What's the potential energy loss equation? mgh, good. What's the kinetic energy equation? Half mv squared. What's the rotational kinetic energy equation? 1/2 I omega squared. Now we don't have any of those things now. You're not given anything else. But now let's substitute. Yeah.
Would be I'm gonna change because it's a full like circle, a full sphere.
It's a solid sphere. So therefore it's mgh is equal to half mv squared. What is the formula for the moment of inertia of a solid sphere? 2/5. So 2/5 mr squared, and then bring the omega squared back there. What is this part? That's velocity squared. You see it? Because velocity is equal to r omega. So this is nothing but velocity squared, and these twos cancel off. So what is left now is mgh is equal to half mv squared plus 1/5 of mv squared. What is half plus 1/5? Oh, you can remove the mass now. So mass doesn't matter. Mass is knocked out. So we have gh is equal to 7/10 of v squared. So what is the v? V squared is 10 gh over 7. How much is this? Tell me. 10 times 9.8 times 2 over 7. What's the speed? At the bottom of the incline. How much? Square root of it? 5.3 meters per second. So you see, when it is rolling, it's going to end up going slower. What if it was not rolling and it was just slipping and going down? If it was slipping and going down, this whole thing is going to be out because no more rotation. Then what will happen? The equation is only this. If the equation is only this, your equation is going to be v squared is equal to 2gh. And what is that? Tell me the answer for this then. 2 times 9.8 times 2. How much? How much? 6 point something. That means it's going to go faster if it slips. And this is something that happens to your car when you hydroplane. As long as the car wheel is rotating, you're safe. If the moment the wheels don't rotate, then everything goes into speed.
So hit the brake.
Yeah, if you hit the brake and if it slips, you have no mistake.
You okay?